Is it visible now? Okay. Okay. So now here we're studying how you calculate expected frequencies. Multiply this row total with the column total divided by the total of all the values. Then you will get all the respective expected frequencies. For example, you want to calculate expected frequency for this particular category. Then just multiply this 1502 with 1473 divided by 7440. So let's do this first one. US, the first extremely important cell. Multiply this 1315 with 1520 and divide it by total value. Then you will get this expected frequency table, this particular table. Now we have to compare these expected frequencies with the true observed frequencies, and then the process will remain same. We do this for all the cells. We will add this, and that will give us the chi-square value. Like no sir, not 1520. The row total is this one. 1315 column total. 1520 multiply by, yeah, if you're doing first one, yeah, 1502 multiply, yeah, okay, so yeah, for first one 1502 multiply by 1520, so you will get this expected frequency 306. Now these expected frequencies we have to compare with the observed frequencies. That's the method in this chi-square distribution. So we have, and what will be the null? The importance of appearance is same across countries, and alternative is the importance of appearance different across countries. Means the importance of appearance is independent of the country, means it's same across the countries, and next is importance of appearance is dependence on country. So this is we say test of homogeneity or independence test. So if you calculate all the values and then divide with your respective expected frequencies, and if you take summation of all the values, the value in this particular situation will be 810. If I'll zoom it out, it's approximately 810 in this particular case. This value we have to compare with critical value, and if you go with the p-value approach, as again you are saying, let's suppose this is the p-value for this particular situation, 0.01. So if our p-value is less than the level of significance, and let's suppose our level of significance is 0.05, then we can say because our p-value is less than the level of significance, we can reject or we do not accept null hypothesis. And what is null hypothesis? The importance of appearance is same across countries. It's not same, right? Means this difference between observed and expected is something important in proportion to expected. So we have to reject the null hypothesis, and analysis of the data shows large differences across countries in the distribution, how important respondents say it is for them to look attractive. Marketers of cosmetics are advised to take note of these differences. That's the conclusion we can take from this particular. So this is how we do in case of contingency, means two variables. So let's do it with Stata software. Now we can do this with Stata software. Okay, so contingency case. Now you can use any data set. I need just two categorical variables. So I'm using the first one, which we are doing in the descriptive case, this college graduate, and this black and race variable and type of school variable. That particular variable I am taking here. So to do this particular association with the chi-square distribution, You will find this option in statistics, summary tables, frequency tables. Within a frequency, there is a two-way table with measure of association. Statistics, frequency table, two-way table with measures of association. It is not working. It might be not because of Skype. Maybe my laptop is because of so many windows are open. Let me close few. Okay. Now take example data set. In Stata, you have example data sets. In example data, select this particular. Okay. NLSW 88. Now, first, let's look upon this data set. We need two categorical variables. Here, there are categorical variables like race, white, black, then married, single or married, then college graduate, not college graduate or college graduate, then industry, then occupations, and so on. So let's take any two categorical variable. Let's suppose I want to see, okay, this one, race and college graduate. Right, black and white. Is the distribution is equal in the college graduate and non-college graduate, or there is some significant difference? Here with the chi-square association, you can't say the degree of association. Like in the correlation coefficient, we say it's moderate, high, based upon the R value. With chi-square, you can just say it's a non-parametric method. That is it that difference is important or significant or not. But how much is significant, that we can't say based upon the chi-square. So first, let's do this particular case, race with college graduate. So for that, chi-square, statistics, summaries, frequency table, two-way table with measures of association. In row variable, I am taking race. Column variable, I am taking college grad. We need Pearson chi-square. Then relative frequencies of row and column. With that, okay, yeah, here we have expected frequencies. Screen is not changing. I don't know what's wrong today. I'm currently on this Stata window where I'm putting these variables. Again, maybe the internet problem I have previous, maybe. Okay, so first I selected my variables, race, and I want to compare it with college graduate. Then I need Pearson chi-square. With that, I also need relative frequencies of column and row, expected frequency that we are discussing right now. So first let's do with these only. So now our table will appear. Now race have three categories: white, black, other, and two categories in college grad, not college graduate, and college graduate. So now you might get confused with these numbers. These numbers are this first one, 1249 is, so I might be taking it, I might be taking time. Just wait. I'm pausing it. Okay, it means it's visible to Nazmi. Okay, thank you, ma'am. So the expected frequency is this 1249 for this particular cell. The way total of row multiplied by total of column for that particular cell divided by total of all the observations. And for this particular value category, the expected frequency is 387. So generally chi-square is difference between observed minus expected frequencies and the square divided by expected frequency. And then summation of all the cells, that's chi-square. Now here you have a row, percentage, and column. Now how I can know this? First one is row. Here they will show you above the table that first one is the frequency, second is the expected frequency, then somewhere it might be because in my laptop and in my screen it's changing, it's visible, but in all of you for not visible for many. It might be it's low today because I'm using both in phone and laptop. So in my phone it's changing frequently, but not in your screens. Then this first one, this third one is the row percentage. It means that out of this total of row, that for white, this total percentage is of the white. Out of that, 74% are not college graduate and only 25% are college graduate. This is the row percentage. Then there is a column percentage that out of not college graduate, total not college graduates, 71% are from white, 28% from black, approximately 1% from other. And here you have a row wise percentages, like in case of black, 82% are not college graduate and 17% are college graduates. In the others, 65% not college graduate and 34% are college graduate. So I was more interested in this difference, that is this proportionate, is it equal in all these categories of race, or there is some difference. So we have, let's suppose we are interested in this particular scenario. Let's see our chi-square value. The chi-square value here is 16.91. And if we do this analysis with p-value, so this p-value is less than, now let's suppose, now first we have to define level of significance. Let's suppose it's on the level 0.05. So p-value is less than 0.05. So we can accept this null hypothesis that these percentages are not same across the race groups. There are differences, and these differences are significant. So that's what we can find from this particular chi-square value in case of contingency table. So this is how we do association for two variables. That's what generally we do in case of categorical variables. I give you the example from the book of a Likert scale. It might be one you at one hand you have a categories, another hand you have a Likert scale variable, or it might be both the variables are categorical. Means you have a categories, like in this particular example, college graduate is the one category and the race is the another category. The one slightest improvement. Let's suppose you want to know the degree of association. Is it a strong or low or moderate? For that, we can use Cramer V. Cramer V formula is to, if it's visible in all of your screens, let me zoom it out. This is to find association, like it's like a correlation between it's, but this is a case of square, so it can't be a negative. Okay, so it's between 0 and 1. If it's less than 0.25, association is weak. It's greater than 7.5, association is strong. And if it's between 2.5 and 7.5, association is moderate. And this is the general simple formula. The row category is -1, and this is the degree of freedom for this particular Cramer V formula. And this is, and also if you have a more number of categories than compared to chi-square, you can use Cramer V. That's a more appropriate technique for interpretation also. So let's put this Cramer V in this particular situation, and let's see the case of association, that how much the association is in our particular case. So for this, you have to just select this Cramer V with the all other tables. Like here we have race, collegiate, our variables, then Pearson chi-square, and here in the end you have this Cramer V. This is to check the association, degree of association. Okay. Yeah. Now we have value 0.08. It means it's less than 0.25. So this association is weak. So we can say there is a significant difference in this proportionate of not college graduate and college graduate among the race categories of race, but this association is weak. It's not too strong. It's weak. It's less than 0.25. So this is how you can work with your categorical variables. And a few limitations or the assumptions of this particular categorical variable. Let me see, I have this particular case, Likert scale is done. Okay, yeah, assumptions. There are a few important assumptions. 570. Just, I'll take 5 more minutes and then wind up this particular class. Yeah, these assumptions you have to take care while you apply this particular chi-square technique. It needs to be categorical, means counted data. Data needs to be from some randomization process, otherwise your distribution needs to be biased and that won't give you the true results. Sample size needs to be proper, and this expected cell frequency, we already said, right, that in your, if it's in your more than 20% cells have at least less than expected frequencies less than 5%, then you can't apply this chi-square test. So these few things you have to keep in mind while you apply this chi-square test. So this is how we apply this particular test, and these are the results you have. Means Stata or any other software they provide is expected frequencies, row percentages, column percentages, chi-square value, and you can use Cramer V to find the degree of association. Since it's a squared distribution, so it's a non-negative thing type of correlation. It lie between 0 to 1. Nearby 0 is weak, means the association is not strong. So I hope this class is useful for all of you who are working on the categorical data. So when you do a categorical data, just give this attention first, guys. When you make the categories, means where you define the categories, but this I have learned from my classes in JNU, that you have to define the categories, means how you selected those categories. You made 5 categories, 6 categories, that you have to define. You need logic behind that, and that for that logic you need to be read a literature or the ground scenario you need to know, so that you can define those categories. It's not a random process that you can make 5 categories. I'm not just talking about the Likert scale, I'm talking about in general. Like in age we make categories 5 groups, like in education we make 7 or 8 categories. That number of categories you have to define, that why you have made this particular, because there are n possibilities, right? I can make category of age 0 to 14, 15 to 30, maybe 0 to 15, 16 to 30, and the results will change. So this justification you have to provide. And if you are using a Likert scale, means it's something like preference or something like this true qualitative variables like honesty, pain, something, means that's not possible to describe in numbers. Then then this is the Likert scale solution we have. That actually this is indirect way to capture information in numbers or this ordinal scale. But then you have to take care about your categories, that if you are making something in a 7 scale or 5 scales, how you are giving ranking to that particular, means what your first and what is your third, what is your fourth. This particular 5 or 7 is why is in the odd, because that order needs to be right. In between we need some average, and then 3 in the left and 3 in the right, means some order needs to be, it's not in the even numbers, right? That's not possible, distribution not possible, so it needs to be in a odd. But 5 and 7 generally we use. Can't make a 9 or something, that's too large, and 3 is too less to capture the gap between the those categories. So that this is the logic behind the 5 Likert scale on 5 scale basis or the 7 scale. It's not a just random numbers. If I can make on 11 basis and it's too much, too complicated, means how can one individual answer that information? How can you generalize 11 scale? So for that reason, to save from those problems, the answer is 5 and 7. But again, put a full attention or take care about that particular categories, whatever you have. So this is when you work with the categorical variable, these things you have to take care of. Okay, thank you so much. So this is done with the categorical variables. So now we will, in the next class onwards, jump to now regression. That's more about something impact and all thing. Okay, so thank you so much. We will join tomorrow at same time.